Okay guys, in the next episode, I am going to show you how to solve this optimization problem. But before going to that episode, because you'll see in that episode, the constraints are going to change their forms. And in this episode, I am going to explain why we can get rid of some of those constraints and how we can change the structure of these constraints. So playing with the constraints before solving this problem is going to make our life easier. So here there is a very, very important result. It's generally true. We are not going to prove it in general, but I'm going to argue why they are true. What do they say? Well, it says the following. There are two statements here. The first statement says the incentive compatibility constraints of the highest type always binds. So who is the highest type here? So when we say highest type, meaning the type who gets higher utility from consuming the same bundle, same package. And if you remember, we already argued this. If you look at the utility function, you can easily say that the type 1 customer's willingness to pay is higher, so he is the high type. Customer type 2 is the low type in that sense. So therefore, incentive compatibility constraint of type 1 will always bind, all right? So what is IC1? It is this one. So it is going to bind. What does that mean? It means binding constraint means the constraint will be satisfied with equality. The second statement says individual rationality of the lowest type will always bind. So here the lowest type, there are two types, right? The highest type is type 1, therefore the lowest type is type 2, I'm sorry. If we had 5 types, well then the highest type and the lowest type would be, not so easy to detect. But again, by looking at the utility functions, you can always determine the highest type and the lowest type. So the individual rationality constraint of the lowest type always binds. So what does it mean? What does that mean? That means the lowest type here, the type 2, and his individual rationality constraint will bind. What does that mean? That means this constraint will be satisfied with equality. All right, well, then what? Well, I forgot to those others, but then IC of lowest type and IR of highest type will be satisfied. Always. What does that mean? That means the IR1 constraint will always be true, meaning whatever x1, p1 whatever this x1, p1 value of this optimization problem, where they satisfy these two constraints, well, this constraint will be true. It will be satisfied. Same for IC2. This will also be satisfied. So as a result of those statements, again, these are always true, not for just this specific example. But as a result of those statements, I can ignore IR1 constraint, IC2 constraint, and I can rewrite this optimization problem by just using these two constraints, IR2 and IC1. All right? And this is exactly what I will do in the next episode and exactly what I will solve in the next episode. But here now, let me explain why these two constraints must be binding, and why are they going to imply IR1 and IC2. Well, let's start with IC constraint. All right, so let's leave everything like this. So let's suppose, I'm going to prove now that IC1 constraint, will be binding, okay? Meaning it's going to be equal. So how can I prove this? So I'm going to prove it by contradiction. So suppose By the way, you can ignore this part of the lecture and immediately jump to the next episode. So for the rest of this episode, I will give you some technical details if you really want to understand the details of these statements. But if you don't want to understand the details of these statements, as I said, these are always true. And so you just take them as given and move on. All right, it's totally up to you. So suppose IC1 doesn't bind. What does that mean? That means suppose P1x1, P2x2 solves this problem, this optimization problem, but IC1 constraint doesn't bind. Meaning 4 squared of x1 minus P1 strictly greater than, it's not equal, it's strictly greater than 4 squared of x2 minus P2. Okay? So suppose this is true. Good. Well, what do I know? Well, I know the following. Because this x1, x2, P2, P1 satisfy those 4 conditions, what do I know is that the following. Look, the x2 and P2 will satisfy this. So 3x1, 3 squared of x2 minus P2. I know that it is greater than or equal to 0. Okay, what do I know? Well, from this, I also know that 4 times square root of x2 minus P2 should also be greater than or equal to 0. Right? In fact, it should be strictly greater than 0. If this is equal to 0, this should be strictly greater than 0, right? Because 4 is higher than 3. But anyway, let's leave it as greater than or equal to 0. Okay, if this is greater than or equal to 0, what do I know? I know that this is also, well, right, they are the same. So that means 4 squared of x1 minus P1 is greater than 0. Okay? So that means the following. So this guy is strictly greater than 0. This is greater than or equal to 0. This is strictly greater than, right? Because I just showed that. And I don't know, this is probably greater than or equal to. Okay? So what I would like to do is the following. Remember, this is the function that I would like to maximize. So here, if I increase P1, I can actually get even higher profit. But the problem is, if P1 is the solution of this optimization problem, if you increase P1, one of those constraints will be violated. And for that reason, P1 is the solution of this optimization problem. All right? But remember, I did some calculations here, and I mean, by assuming for a contradiction that this is true, I realized that, these are also true. Well, now I'm going to argue the following. If I increase P1, in fact, slightly, not too much, slightly increase P1, I will actually not violate any of those constraints. How so? Well, if you look at this one, if I increase P1 slightly, not too much, slightly, it will still be greater than or equal to 0, but it's not going to be less than 0. All right, so increase P1, but very small amount. Well, if I increase P1, I am keeping x2, P2, x1 all the same. All right, they're fixed. So therefore, this constraint will still hold because I am not changing x2, I'm not changing P2. What about this one? Well, remember, this is strictly less than this one. So therefore, if I increase P1, it's going to be maybe equal to. But that means IC1 still holds. And finally, this guy. Well, here, this part is the same. If I increase P1, this part will be even smaller. So this constraint will always be true. So what does that mean? That means if I increase price of package 1 slightly, none of the constraints will be violated. And so that means the P1 actually is not the optimal price for package 1. So that contradicts with the assumption that P1, X1, P2, X2 is the optimal solution of this maximization problem. All right? So, because it can't be, This assumption should be wrong, therefore. So that means the IC constraint of the highest type must bind, meaning it should be equal. So this is how we prove the first statement. Now I'm going to prove the second statement. But before I prove it, let me go back to the original scenario where everything is greater than or equal to. All right. But we already proved that this has to be equal. So leave it as is. And now I'm going to prove the second statement. And the third statement, by the way. The third statement is easier. How so? Well, look. If this guy is 3 squared of x2 minus p2 is greater than or equal to 0, this guy is also greater than or equal to 0, right? So 4x1, 4 squared of x1 minus p1 is equal to this, which is greater than this, which is greater than or equal to 0. So that means automatically, if this is true, this must be true. All right? So once again, if IC1 constraint binds, well, then the IR constraint, the individual, meaning, let me put it this way. If consumer of type 1 is willing to buy his own package because his utility of buying his own package and the second package are the same, well, that means his utility of buying his own package should give him at least 0 utility. Maybe positive, we don't know that, but it should give at least 0. So therefore, we can actually ignore this constraint because it will be true. All right? All right, now let me prove that the IR2 should bind. So suppose, once again, P1, P2, X1, X2 optimal solution to this problem. And 3 squared of x2 minus p2 is not binding, which means it's strictly greater than 0. Okay? All right, so what do I have? Well, remember this constraint is binding. So if you rearrange this constraint, send p1 to the other side, pull this 4 squared of x2 to this side, what I'm going to have is the following. 4 parentheses squared of x1 minus square root of x2 is equal to p1 minus p2. Agree? Yes. Okay, what else? Well, you know what? If this is p1 minus p2 is equal to this, I know that this is greater than or equal to 3 times square root of x1 minus square root of x2. Agree? But remember I said, if the monopolist is going to offer 2 packages, those 2 packages should have different x's and different p's. I mean, you cannot charge the same price to 2 different packages, or you cannot, charge different prices for the same amount of x1 and x2. So meaning square root of x1 minus square root of x2. So this will never be 0. So this will never be 0, all right? This is either positive or negative, but they're never 0. They can't be. I mean, this can't be optimal, all right? So therefore, I can conclude that 3 square root of x1 minus x2 is in fact strictly less than 4 times this difference. So what does that mean? That means now 3 square root of x1 minus square root of x2 is strictly less than p1 minus p2. So now I'm going to send x2 to the other side and p1 to this side. So if you rearrange this, it means 3 square root of x1 minus p1 is strictly less than 3 square root of x2 minus p2, which is very much like this one. But I just shown that if this is true, well, this will never be equal. It's going to be strictly higher. All right? What else? I assume that this is strictly higher. And this one is greater than or equal to. I don't know. I don't care. So I'm going to do a similar argument. So if P1, P2, X1, X2 is optimal, that means if I increase P2, I should be violating some of those constraints. At least one of them. However, if I increase P2, look at here, it's not going to change this constraint, so it's going to be true. Here, if I increase P2 slightly, not too much, it will still be greater than or equal to 0. So this constraint, IR2, will continue to hold. Well, this constraint, remember my constraint was greater than or equal to. So if I increase P2, this will be even smaller. So therefore, IC1 constraint will still be true. And finally, IC2 constraint. Well, if I increase P2 a little bit, not too much, this is going to be greater than or equal to. So what does that mean? That means, in fact, if this is true, I can slightly increase P2 without violating any of these constraints. That contradicts with the assumption that P1x1, P2x2 are optimal. So therefore, some of the assumptions are wrong. Well, here, what is the assumption that can be wrong is this one. So this must be wrong. So that means the individual rationality constraint of the lowest type, which is this one, has to be binding. Well, finally, what I would like to say is the following. If this is binding, all right, so if it is equal to 0, all right, so that's 0. Well, what about this one? So this is the same. This is the same. Okay, guys, so if I need to summarize, I just proved that the incentive compatibility constraint of the highest type, which is type 1, has to be binding, all right? And so this has to be equal. And the individual rationality of the lowest type, which is type 2, must be binding. So this must be 0. And if you remember, I proved the third statement for type 1. So the individual rationality constraint of type 1 must also be must not be binding, which means this is strictly positive. And if you remember, this is because IC1 constraint is binding. So if IC1 is true, well, then this term is going to be strictly positive. And so IR1 constraint will be satisfied. And so you can ignore this constraint. And then finally, I want to show that this is true. All right, so given that IR2 and IC1 are true and this one is true, well, how can I prove that this is going to be satisfied? So suppose for a contradiction, this is not true. What does that mean? That means, well, don't forget, this is an optimization problem. X1, P1, X2, P2 satisfy all those constraints. Some of them are binding, some of them are not maybe. But if this constraint if this is not true, that means 3 square root of x1 minus p1 is equal to this 3 square root of x2 minus p2, which we just shown that it is equal to 0. All right? So what does that mean? That means 3x1 minus p1 is equal to 0. Okay, very good. Well, however, what I can prove is the following. So here, if you add x1 to both sides, a square root of x1 to both sides, I'm going to have 4 square root of x1 minus p1, which is equal to square root of x1. Agree? Okay, so let's keep this in mind. What else I would like to do? Because individual rationality of the second type is true, add square root of x2 to both sides. So I'm going to have 4 square root of x2 minus p2 equals square root of x2. All right? Okay. What else? Well, remember 4 square root of x1 minus p1, which is equal to square root of x1, is equal to, because IC constraint for type 1 is is binding, 4 square root of x2 minus p2, which is equal to x2. This is what we just shown. So that means x1 must be equal to x2. But remember, once again, the solution of this optimization problem cannot be the case that x1 is equal to x2 or p1 is equal to p2, because if this is the case, we know that both types are going to choose only one of the bundles. So x1 is or has to be different than x2. So we get a contradiction because this equality cannot hold. So that contradicts with the fact that, or with the assumption that these two guys are equal to each other. So they shouldn't be. So we know that this is greater than or equal to this term, and we just proved that they can't be equal. So therefore, this guy has to be strictly greater than this guy. So that means the IC2 constraint will be satisfied if IC1 and IR2 constraints are binding. So that means we can ignore IC2 constraint. We already knew IR1 constraint can be ignored. And so the third statement, is verified. So the bottom line is that this entire optimization problem can be simplified. Instead of worrying about 4 constraints with inequality, we can actually rewrite this maximization problem with 2 of these constraints with equality and then solve it. This is what I'm going to do in the next episode.